Now, we just did two-dimensional vectors, but, of course, as you're probably aware, we live in a three-dimensional world, so we got to deal with three-dimensional vectors, too. So there's the Salem Convention Center. You'll notice those struts that hold up the roof there go off at odd angles into three space. So, a lot of problems we do analyze in two dimensions. Like a truss bridge, you do it that way. But the struts that are holding up that roof or the frame on that vehicle there, they're three-dimensional, so we have to handle them that way. Okay. So this is another thing that we got to deal with. We got to do 3D vectors. Now, I was mentioning when I do 2D vectors, I tend to just look at it and say, this force is pointing that direction, and I handle it that way. I use a more formal approach with 3D because it's more complex, and it's harder to do that sort of approach with. So when I'm doing three-dimensional problems, I tend to be kind of more, I don't know what the right word is, formal in how I do it. I have a set method, and I just do it that way, and that works the best for me. Okay, now this is on page 160. Now I'm hoping you all have that note packet. If you don't, you definitely need to have it. And so that's available at the bookstore, right? So you do want to have this thing. So when we have three-dimensional vectors, we're often writing them out on a flat piece of paper. So there's a convention for that. We write up the axes like that, as you see in front of you there. And they're based on what's called the right-hand rule. Now, the right-hand rule says if you take your fingers and point them in the X direction, curl them towards the Y, your thumb points in the Z. All right? So fingers in the the right hand in the X direction, curl them in towards the Y, your thumb then points in the Z. That's the right-hand rule. Okay? And this is how we draw up our vectors, like that. Now, I think in physics, they might do it more like that. A little different way of orienting the axes in three space, but they both represent the same thing, okay? So what we're going to do now is have a vector that goes out into three space. We're on page about 160. So if you're in the packet, probably worthwhile to go over this just for a minute. If you're in the packet, the first, actually with all the extra pages I put in there, it's about 60 pages are homework. You got to flip through that till you start getting into the 100s. When you get there, look for page 160. That'd be the way to do that. Yeah, it's kind of a weird system, a goofy system. I don't quite know what, but that's how it works. Okay, we good? Okay. And if you don't have that packet, be sure to get to the bookstore and get one. The lines ought to be coming down there, and you're going to need that. Okay. And I'm pretty sure I mentioned that Monday, I think. Okay, 160. It's not in the stapled handout. It's in the packet. That's where it's at. Okay. Okay. So we use the right-hand rule. Now, when you do a vector that goes off at an angle in three space, like that strut, like this thing here, it's, in the photograph, whoops, that's not going to work, is it? I better do it on this screen. Here we go. That's just going off at an odd angle in three space, okay? So when you think of a 3D vector, what you're going to do is draw a box, and the vector sits in the box. The tail of the vector is on one corner of the box. The head of the vector is on an opposite corner of the box. So that's how that works, okay? So we're thinking something like that, where we have a nice rectangular box and we have a vector that goes from one corner to the opposite corner in the box. And that is how these vectors work in three space. Okay. Oh. There it goes. Something like that, okay? And the reason I like to think about it that way, and this particular box is oriented like this so you can see it. So that's X. Right hand gets you the Y. There's the Z. Okay. X, Y, Z. Because the edges of the box are the three components of the vector. Okay. So the X, the Y, and the Z components then are the three X, Y, and Z components of the vector. That's how we think about a three-space vector. Okay. So are we good with that? We got any questions? Doing all right? Right now, a unit vector then is a vector with a magnitude of 1. Unit vectors are used to show direction. So we talked about ij, and then there's also k that act in the x and y and z directions, but you can also have a unit vector for any vector in 3 space. So I can take that angled vector that I'll put a squiggly line in blue on that vector. I can turn that into a unit vector, or I can make a unit vector that'll have a magnitude of 1 and points in the same direction as that vector, okay? And the way I would calculate that is I would take the vector, let's call it A, and I would divide it by its own magnitude, and that's how I would come up with a unit vector. So the unit vector A is equal to the vector A divided by its own magnitude. Now, I bet if we were in a math class, your instructor would probably write that out like that. Is that what they do? I'm not going to do that, though. That's not how it's done in engineering books for whatever reason. We put a vector hat on the vector. We put nothing on the scalar. That's how we do it. It's different than the math classes, I know. All right. So what A is then is it's the x component of A plus the y component of A plus the z component of A. And I can go ahead and write that out as AX is a magnitude times I, which shows me the x direction, AYJ, and AZK. I, J, and K are the x, y, and z components. Okay. So are we all right with that? That's how I write out a 3D vector. It has 3 components now, as opposed to the 2 components we were just talking about. All right. Now the magnitude of the vector A is just A. I don't bother with this stuff as they do in math. I don't do that, okay? So I don't do it that way. Well, if you look at an engineering book, they won't do it that way. So if I want the magnitude of the vector A, I can do the theorem of Pythagoras in 3 dimensions. I just take the 3 components, I square them, add them up, and take the square root. That will get me the magnitude of vector A. Okay. You all right with that? Questions on that? All right. So what I've got here now is I have a vector A in 3 space. It has x, y, and z components. I can find the unit vector A by taking the vector A and dividing it by its own magnitude. And to find its magnitude, I take the square root of the sum of the squares of the 3 components. That's a 3-dimensional theorem of Pythagoras is what that is. All right? All right, now let's look at the relationship here between the components and the total vector and the angles that the vector makes with the x, y, and z axes. Okay, let's have a look at that. And this gets a little bit tricky to draw. So what I'm going to do is take the one that I can see the most readily and show you what's going on with that. So what I have on that sketch on the upper right is I have the vector A going from one corner to the other in that box, one corner to the opposite corner. And then I have let's look at the z component of that vector A. That's the edge of the box that goes in the z direction. So what I'm looking at is this, the length of the vector, and that edge right there going in the z direction. All right. Now, if I take a line and I run it across the top of the box, what's that angle right there between the z component and that line running across the top of the box, do you suppose? One would hope it would be 90, right? Because that top of the box is in what I would call the XY plane. Okay? Mathematician might actually call it the Z plane, but I'll call it the XY plane. And I've got a line in the Z direction. So I got the Z axis, the XY plane. That's going to be a 90-degree angle in there. Y'all with me there? So what that gets me is a right triangle, doesn't it? Okay? So here's my right triangle. And what's going to happen here is the vector A is the total vector. That's actually going to be a hypotenuse. The Z component will go up like that. So there's AZ. Here's A. And then I've got a line across the top of the box, and that's going to be a 90-degree angle there. So what that means is if I want to find this angle in here, and why don't I just call it gamma, just for fun, I'll call that angle in there gamma. The way I can find that angle is I can do an inverse cosine. Cosine of gamma will equal AZ over A. You all with me there? Because what I've got is I've got the hypotenuse, and I've got the adjacent side. If I take the adjacent side of the angle and divide it by the hypotenuse, that's the cosine, right? Okay. So the inverse cosine of AZ over A gets me that angle. I'm going to call that gamma. All right. So what's happening here is I've got this relationship where if I know the vector itself and the magnitude of the total vector, that would be A, and I know its three components, I can go ahead and find the angles that the vector makes with the X, Y, and Z axes. That relationship holds for all three components and the three different axes. With the sketch I have drawn, it's easiest to see it for the Z direction. Okay? But it also holds for the X and Y directions.
For the X and Y directions, we have to find the projection of the X and Y plane.
Yeah, it'd be the same process. You just kind of reorient the geometry. Yeah, it's just with these sketches, it's going to be really tough to illustrate that as well as I'd like. You know, as I say, it's easiest to see for the Z, but with the x-axis, you call that angle that the vector makes with the x-axis, you call it alpha. That would be the x component and the yz plane. The angle with the y-axis would be beta. The sides would be the y-axis and the xz plane. You know, that's how that would work, okay? So we can pull three right triangles out of that, do three inverse cosines, and come up with those three angles. And we call the angles that the vector makes with the x, y, and z axes alpha, beta, and gamma. Okay? So there they are on that sketch. So the deal is now we have a relationship between the vector and the angles that it makes with the x, y, and z axes. That's what we've got when we do this. Okay? We got questions on that? Okay. All right. Now let's see what we can do with that, because we can get some practical information about these vectors from that fact. What we can do is take the vector A and divide and take the vector AX, AY, AZ. Okay. So AX, AY, and AZ, and divide each one of those by the total magnitude, which is A. All right. And what we'll get are the cosines of the angles that the vector makes with the x, y, and z axes. But if we take each one of those components and divide it by A, what we've got is a unit vector, see? The vector A divided by A, which would be AX over AI, AY over AJ, and AZ over AK, that's the unit vector. Okay? That's how you make a unit vector. You divide the total vector by its own magnitude. Okay. So what you've got when you have a unit vector is you have what we refer to as direction cosines. You've got the cosine of the angles that the vector makes with the x, y, and z axes. That's what you've got. Okay? So do we have questions on that? You doing okay with that? All right. So that's a key relationship there. Now another thing is the unit vector has a magnitude of 1. What that means is the unit vector, if you square each of the components and add them up, that should be 1 squared, which is 1. So that gets us into another little relationship here that's kind of handy to know. If you take the squares of the cosine of alpha, beta, and gamma and add them together, they should add up to be 1. What that means is if you don't know one of those angles, you can find it if you have the other two. Okay? But the key relationship here is that when you have a unit vector, you have what we call the direction cosines. All right. Now let's say you know the alpha angle, or the angle alpha, I'm sorry. If you're given the alpha angle, what shape would it describe about the x-axis? So here's my 3-space axis system. If I know alpha is 30, what do I know about the total vector? What does it look like when described around the x-axis? What would it be? What shape would that describe? Right triangle, but a little bit more too. What if I don't know anything else? All I know is alpha. What happens to the right triangle? Cone, yeah. Okay. So it's a right triangle revolved around the x-axis. Yeah. So if I know what alpha is, if alpha is 30, I've got this 30-degree angle, and I know that it extends somewhere around the x-axis. So what I'm going to end up with is a cone, right? So I had a student, and this was a long time ago, right when AutoCAD was starting to go 3D. He plotted up one of the vectors we were working on. So there's the 3 angles, alpha, beta, and gamma. Alpha is 69.3, beta is 111, and gamma is 30. He plotted 3 cones around the x, y, and z axes. And sure enough, they intersected on one line. There's that vector, okay, where those 3 cones intersect. So it's not like you can just pick out any 3 angles and make a vector out of it. They have to have a relationship that conforms to that. They have to intersect on a line, okay? And the way you describe that is with this square relationship. So if you know 2 of the angles, you can find the third using this relationship here. And those 3 angles, if they're valid, when you create 3 cones based on them, they should intersect on a line, and that's the vector. Y'all good with that? Okay. Questions there? Doing all right? Okay. All right, let's look at an example of this. And this is on page 180. All right, now, who doesn't have the book? Just be honest, tell me. 1, 2, because how many of you? What I'm going to do, I don't want to put you through this without the book. How many? I'm going to run copies, but I'm not going to do it twice. So who doesn't have the book? 1, 2, 3, 4, 5, 6. Come clean, it's okay. We got 6? Okay, I'm going to run 6 copies. I'll be right back, okay? I'll pause this. I'll be right back. All right, there we go. So there's page 180. So what we're going to do, we're going to add 3 vectors together and get a resultant, kind of like what we were just doing in 2D, but now we're going to do it in 3D. All right, so let's have a look at this. I've got 3 vectors, F1, F2, and F3. F3 is going right in the Z direction, so that one's pretty easy. But let's get alpha, beta, and gamma for F1 and F2. And all you got to do here is look at how the vector is tied into the axis. So for F1, right there, that's 53 degrees with the y-axis, isn't it? So just look at those dimensions and figure out what alpha, beta, and gamma are for each of those vectors. So that's step one. What we want to do is add these vectors up and get a resultant. And the way we're going to do that is break them into components, just like what we did with 2D vectors.
Principal angles given, the angles between the vector and their component.
Yeah, the vector and the axes, yeah. Those are dimensioned there.
Okay.
And what we want to do is learn how to read this stuff. Part of this class is going to be learning how to read these dimensioning systems that we use. You know, they're kind of the system you have to learn. So that's how I'm showing the angles. I'm dimensioning them with the 3 axes. So that F1, it looks like 53 with the Y. How about with the X? What do we got?
31.9.
Yeah. How about with the Z?
64.
64. Okay. So that's all I want you to write down. Okay. Okay, now see how those dimensions are connecting to the different axes? So they're, and frankly, some people have just better innate skills at this than others. So if it's not something that comes naturally to you, you kind of have to train yourself to do it. Okay. We okay with that? You all? Okay. I'm just looking at how the vector is connected to the different axes is what I'm looking at. Okay. All right, so I got 131.9, 53, and 64, and I got 61, 149, and 80. Good? Okay. Now, once I got the angles, see, I'm looking at those angles, and I've got the magnitudes up here, 500 for F1, 800 for F2, and 700 for F3. I can build Cartesian vectors now. And I'm just walking through it step by step for F1. I've got the unit vector for F1 is the cosine of the angles, alpha, beta, and gamma times ij and k. I get that broken down. See, I got 3 significant figures there, so I'm pretty good. That's the unit vector. By taking the cosine of the angles with the 3 axes, I get the unit vector. Then I scale it up by the magnitude. The unit vector has a magnitude of 1. So if I take a vector with a magnitude of 1 and multiply it up by 500, I'll have a vector with a magnitude of 500, where the components are proportioned out properly in the x, y, and z directions. That's what I'm doing there. And that gets me F1. Of course, I like to check my work, so I take the square root of some of the squares, and sure enough, that comes out to be 500, so that's looking pretty good. All right. Y'all with me there? Okay. You two can do statics, so why don't you do that for F2, okay? See if you can do that. I've got it set up over there on the right, and just look at the steps on the left and imitate them. That's how you do this 3D stuff. Step, 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 and just walk down through it, okay? let me know, or ask your neighbor. Just follow the steps on the left, go on the right. Mm-hmm. Yes, the magnitude of F2 is 800 there. You see it there in the sketch. You just multiply it through. You'll get into something like that. 388 minus 686 and plus 139.
Why did you put a negative in front of the cosine of 61?
Okay. All right, so, okay, the cosine of 61,
It's coming out like,
kind of off to the left, or, well, as we look at it to the left of the x-axis, is that kind of what you mean?
yeah.
Okay, now in 2 space, I look at angles and go negative, positive. In 3 space, I don't. If that thing is anywhere along that cone, it's going in the positive x direction. Okay, and so 3 space becomes much trickier to look at it visually and give it a sign. It's on that cone right there. And anywhere along that cone, if it makes a 61-degree angle with the positive x-axis, it has a positive x component. So all I'm going to do is just look at the angle with the positive axis and use that and rely on the,
So I thought that would be negative x-axis and the positive x-axis would be going like, so there's like z and y, and I thought like the positive x-axis would be going into the opposite.
that would be right-hand rule anymore.
Okay.
Because x, throw my fingers into y, z goes up. That's normally how we draw the positive axes there.
Okay.
Might be different than math and physics too, which might complicate things. Is that good?
Yeah.
Okay, so the kind of the upshot of that, or the main point is that you just look at the angle and do a cosine of it. Don't put your own signs on it. Just use the angle and do a cosine. And see that what's the one that's going to have a negative? When they're bigger than 90, that's when they have a negative, because now they pull back in the negative direction if it's greater than 90. Okay. So the good news is it's a rather straightforward process. If you got the angle with the positive x-axis, just take a cosine of it and go with it. That's all you got to do. Okay. Okay. We good with that? Any other questions on that one? Okay. Okay. I did F3 for you there. It's it's just in the z direction. That's all I had to do. Okay. Good. All right. Now I've got all those vectors broken up into their x, y, and z components. I just add them up. So again, I just put them in rows. I'm going to add up the columns. That's what I'm up to there. So I'm going to add up that column, I'm going to add up this column, and I'm going to add up that column. And I get the resultant vector. Yeah, what I want to do, an extra part of this problem, just kind of to do something extra, was to find alpha, beta, and gamma for the resultant vector. To do that, that's why I did that last step. Okay, so the resultant there, I'm just adding up the columns is what I'm doing. Okay, so I get 54i minus 385j plus 1058k. That's what I get by adding up the columns. The square root of sum of the squares gets me the resultant force. It's 1,127 newtons. Okay. Now so that's the magnitude of the resultant. So if I apply those three forces to this point, the net pull that point is going to feel is 1,127 newtons. That'll be the net force on the point. Now I might be interested in the direction of that force. So to get that, I might want to get the angles that that force makes with the x, y, and z axes. So I can do that to find alpha, beta, and gamma for the resultant vector. What I would do is I would turn it into a unit vector. The way I do that is I divide it by its own magnitude. Now I have the unit vector. Now what the unit vector is the inverse is the cosine of alpha, beta, and gamma. So I can find alpha, beta, and gamma. Now I can get an idea of which direction that vector points. That's what I can do with the last step here.
It's just the inverse cosine of those in
Right, yeah.
those three numbers. Oh, that's cool.
Yeah, that's it. Okay. All right. Oh, I still have that. We good with that? So
Scroll up for a second.
what's that?
Can you scroll up for a second?
Yeah, sure. Okay. Just here or the next one up? That one? All right. You good? All right. All right, so I've got that unit vector. When I divide through by the 1,127, I just take inverse cosines of those three components, and I'll get alpha, beta, and gamma. So alpha is 87.3, beta is 110, and gamma is 20.2. So that tells me what direction that resultant vector points. So the key relationship there is that relationship between the unit vector and the angles. That's the key relationship. If you have the unit vector, you can get to the angles. If you have the angles, you can get to the unit vector, because the unit vector is the cosine of the angles with the x, y, and z axes. So you're doing all right with that? And then you can kind of make a sketch there. It's hard to make an accurate 3D sketch though. They're not to scale because they're, by their nature, they're distorted. Because you're looking at a three-dimensional axis system on a flat two-dimensional piece of paper. All right. Now let's. So we got any questions on this stuff? Okay. All right, I'll get you some of these to do. So we're gonna have a few of these. So do Monday, and that'll be the 13th. 122, do graphically, and I gave you graph paper for that one. And that's on page, I think it's 1A, isn't it? I can't remember, but I think that's it. 1A? Okay. That one's graphically. Now, the next two you do not do graphically, you do them analytically. So how about 131 and 2? And then let's do a three-dimensional problem also. How about 141? So these will be due Monday. We'll go over them Friday, right? So 141. Now a lot of these I've written up for you. 141 is on page 2A. So that one's good to go for you. I'm not sure about 131 and 2. I don't know if I wrote those up or not. I don't think I did, but I might have. Yeah, they're on the next. Are there? Is there like a page of those?
132 is there. I don't know. 132.
Okay, 132. So 132, is that probably 1B then?
Yeah.
Okay. So you only really have to write up one of these. The others in the packet, you have the pages for if you buy the packet. Okay? Good to go. So we'll go over these on Friday. All right. Okay. All good?